Applications of differential calculus. So you have hopefully watched the TED Talk video, or you will watch it soon. Please remember that as you watch that TED Talk video, you need to write a brief report on it, plus do a little bit of research and find one more application of differential calculus. Just write a 1/2 to 1 page report on that and submit it on Turnitin. It's not meant to be a huge assignment, just so that you have a little bit of background about what calculus can do for us in the real world. So what we are going to concentrate on as far as applications is kinematics, rates of change, and optimization. So these three main ideas. Okay, right away we have this opening problem in chapter 17. Michael rides up a hill, he's on his bicycle, rides up a hill and down the other side to his friend's house. So we can imagine what's going to happen here. It's going to take him longer to ride up the hill than it does to ride down the hill to on the other side. So we can see the dots on this line graph right here that show us how far in a picture he is after 0 seconds, after 5 seconds, so 0 seconds, after 5 seconds, after 10 seconds, after 15 seconds, after 17 seconds, and after 19 seconds. So you can see in this portion of the trip, that's the downhill part, he's going a lot faster. This portion of the trip, he's going quite a bit slower, and in particular, slower from here. Okay, so let's take a look at what this looks like on a graph. The distance Michael has traveled at various times is given by the function s of t. So this is representing what's happening pedaling up the hill and then down the other side. 1.2 t cubed subtract 30t squared plus 285t. This distance is in meters, and it's from 0 to 19 minutes. Okay, so 0 to 19 minutes. I may have said seconds up above, I'm not sure, but it's in minutes. Things to think about. So this is a cubic function. We can see that by the 3 here in our highest exponent. We can also see it's a cubic function by the shape of the graph. Okay, it has 2 turning points. Explain why s of t should be an increasing function. So last chapter we talked about increasing and decreasing functions. This is an increasing function because as time goes on, the distance increases. Okay, so basically as time goes on, the distance increases, and graphically we can see that the y value is going up as the x value increases. So that's an increasing function. B, can you find a function for Michael's speed at any time t? Okay, so this is an example of what calculus is used for. We can find the speed. The speed is going to be the first derivative. So let's take a look at that. First derivative. This would be 3.6t squared subtract 60t plus 285. Okay, so at any time t, we could plug a t value in. We could plug however many minutes in here to this derivative function and see his speed. Okay, this makes sense because the derivative function is the slope of the tangent. So if we choose this time here, 2.5 minutes, and we draw the tangent line, his speed is the slope of that tangent line, which is given to us by this function. Speed is distance divided by time. And so this absolutely makes sense. Distance divided by time. Okay, so distance divided by time is speed. So we can calculate that. Okay, change in distance change in time. And that's exactly what the slope of this line is going to give us. Michael's acceleration is the time at which his speed is changing with respect to time. Okay, so the acceleration is the rate of change of his speed. Okay, rate of change of that first derivative. So we're going to be able to calculate the acceleration with a second derivative. So 7.2t subtract 60. Again, at any point in time, we can substitute that t value in here, and we will be able to see his acceleration. So can you find, in part D, can you find Michael's speed and acceleration at time t equals 15? Well, we would substitute 15 in here for t to calculate his speed. You can go ahead and do that. And we would substitute 15 in here to calculate his acceleration at that point, at his 15-minute mark. And E, at what point do you think the hill was the steepest, and how far had Michael traveled to this point? So where do you think the graph is the steepest, or the hill is the steepest? Okay, so we're looking for a maximum. Looking for a maximum at that point. So I want you to think about, put some thought into that. What is going to happen? How could you tell?